Your database told you the payment went through, and 11 milliseconds later the power died in that rack. When the machine comes back, you have to answer a question you have probably never had to answer out loud: is that payment still there? Not the version you saw on your screen. The version on the platter, which is the only version that survived the night. If your honest answer is a shrug, you are about to find out what a shrug costs. You already know the shape of the sphere even if you have never named it. Under your tables sits a file, and that file is not one flat sheet. It is thousands of fixed size blocks, and a single ordinary update to a single ordinary row can touch several of them at once. Your money row moves. The index that finds your money row moves. A free space map somewhere moves too. Now picture the lights going out with two of those three changes safely down and one still sitting in memory. You have no torn payment to point at. You have something quieter and worse, a table that disagrees with its own index, and not one error message anywhere. Park that question for a moment, since it is the one your own on-call rotation asks you at 3 in the morning. Why should a database ever be allowed to leave your data half-changed? And the standard answer should bother you more than the danger itself. You fix this by making your database write every single change twice. Twice. You pay for the disk, you pay for the input and output, and you pay again for bytes you already paid for once. Yet the engines that work this way are the fast ones under load. You have inherited this arrangement rather than chosen it. Every relational database you have run in production does it, and it costs you real money on every write your customers make. Have you ever actually measured what that doubling costs you? So it is worth knowing precisely what that money buys you, since the same reasoning governs whether you can trust a queue, a ledger, or your own careful file writes at 2 in the morning, which is why the idea travels much further than databases. Here is the rule itself, and it fits in one sentence. Before your database is allowed to change a data page, it writes down what it is about to do, and that description reaches stable storage first. The description is called a log record. The file those records live in is the write-ahead log, and the name is the entire idea. The log runs ahead of the data it describes. In other words, your database announces what it is about to do before it does it, and it states its intention in a place that survives a power cut. Notice how much work the phrase stable storage is doing in that sentence. It means the device itself has confirmed the bytes, not that your write call returns successfully. Those are different claims, and the space between them is where your data goes to die. Hand bytes to the operating system, and they usually land in the operating system cache, in memory. The call returns. Your code feels successful. The bytes are still in memory when the power fails. The system call that closes that gap is FSINC, and what it does is refuse to answer you until the device confirms it holds the data. Which of those two does your own code actually check for? Which turns commit into something much narrower than you may think it is. In other words, a commit is not a promise that your table on disk is current. It is a promise that one particular record, what we call the commit record, is durable in the log. The page can wait. It is allowed to sit in memory as a dirty page for minutes after you were told your transaction was safe. Your database is, in a very precise sense, allowed to lie about the page for as long as it never lies about the log. Does that make you more comfortable, or less? Note, none of this is folklore or local custom. The design was written down properly in 1992, in a paper called Aries, by Mohan and colleagues at IBM, and its vocabulary is the vocabulary your database still uses today. PostgreSQL, MySQL through InnoDB, SQLite in its journal modes, Oracle, and effectively every serious storage engine ships some dialect of what that paper described. Notice that the words survived 30 years of hardware change, which is unusual enough to be worth trusting. So why write everything twice? Take the naive path first, the one you would reach for yourself. Skip the log entirely, and just be careful about the order in which you write the data pages. Write the row, then the index, then the map, and hope. But that is not a fix, and the reason is arithmetic rather than taste. Those 3 pages live in 3 different places in the file, so making them durable means 3 separate trips to a device that charges you for every trip it makes. Now compare that with the log. Here is what happens down at the device. A log record has exactly one destination, the end of the file. Every write is an append at the tail, so the head or the flash controller stays roughly where it already sat. The data pages behave the opposite way. They scatter across the file in whatever order your customers touch rows, which is a random write pattern, and random writes are the thing that actually costs you time. Put numbers on that, since the numbers are the whole argument. A spinning disk needs something like 8 milliseconds to move its head somewhere new, because the head has to physically travel, and the same disk will stream sequential data at well over 100 megabytes a second. So 3 scattered page writes cost you roughly 25 milliseconds of pure waiting, while one small sequential append plus one flush costs you a fraction of that. You are paying twice in bytes so that you can pay once in seeks. That is the trade, and now the title makes sense. Writing everything twice is faster than writing it once. That flush is still the expensive part, though. One flush for every transaction would cap you at a few hundred commits a second on that same disk, which is nowhere near what your traffic needs. How many commits a second does your device really allow? So engines batch the cost. Transactions that commit within the same instant share one flush, a trick called group commit. The engine will wait a couple of milliseconds, collect whatever commit records show up, then pay for one trip to the device on behalf of all of them. Your durability stops being a private bill and becomes a shared one. So what exactly goes into one of those records? You have two honest options, and real engines use both. A physical record names a location. On page 4002, these bytes at this offset became those bytes. A logical record names the action instead. This row in this table had its balance reduced. Which one would you rather replay after a crash? The physical form is blunt and safe, because replaying it works by copying bytes and needs no understanding of your schema at all, which is why recovery can run before the database is fully awake. The logical form is far smaller, since one short sentence stands in for a page of changed bytes, but it has to be replayed by code that can interpret your tables. Most engines settle in the middle and record physical changes to logical structures, the compromise the Aries paper argued for. There is one failure that pushes engines toward the physical style, and it sounds impossible until you meet it. What happens if the power fails in the middle of writing a single page? A page is commonly 8 or 16 kilobytes, while the device writes in sectors of 4 kilobytes or less, so one page write is really several device operations wearing a single name. Lose power between them and the page on disk ends up half old and half new, a torn page, and the sequence number stamped on it may sit in the half that never landed. So recovery cannot trust the stamp it needs in order to decide whether to skip. MySQL therefore writes every page into a small holding area first, the double write buffer, which keeps a spare clean copy to fall back on. PostgreSQL takes the other route and logs whole page images the first time a page changes after each checkpoint. Same failure, two different bills, and both of them chosen on purpose. Now the part all of this was for. Your machine dies mid-transaction, the power comes back, and the engine starts up knowing nothing about what was in flight. The process has two steps and both read the same file. It replays the log forward from the last known good position, asking one question of every record: did the transaction that wrote this ever commit? If it did, redo the change, whether or not the page already shows it. If it never did, undo it, and roll it back out of the table so no half-finished transaction is left visible to anyone. Case in point, when PostgreSQL comes up after an unclean shutdown, it prints a line saying it is starting recovery, then replays from the most recent checkpoint until it reaches the end of the log. On a busy system that takes seconds, sometimes a few minutes, and you can watch it happen. What you never see is the interesting part, which is that nothing in your tables was trusted until the log had spoken. Which raises the question that separates people who have read about this from people who have operated it. What happens if the machine crashes again during recovery, halfway through the replay? Recovery has to be safe to repeat, so every page carries the log sequence number of the last record applied to it. Replay reads that stamp on the page, compares it against the record in hand, and skips anything already applied. So applying it twice changes nothing at all. The property has a name, idempotent, and it is why a database can crash 5 times in a row while recovering and still come up correct. There is one more question a careful listener asks immediately, and you may already be asking it. If every change is logged, why is your disk not full by now? The answer is the checkpoint. Every so often the engine flushes the dirty pages it has been holding, then writes a record that says, in effect, everything before this point is safely in the data file. Recovery never needs to look further back than that mark, so the log before it can be truncated or recycled. Checkpoints bound how far back recovery reads, and that bound is the only thing stopping the log from growing forever. Walk one transfer through the whole machine and you can see every piece cooperate. You move money between two accounts, so 2 rows change. 2 log records go to the tail of the log, then a third record says the transaction committed, and the engine flushes. Your client gets its acknowledgement at that instant. Both account pages are still dirty in memory, and they may stay that way for a while, because nothing about correctness needs them yet. If the power fails now, replay finds the commit record, redoes both row changes, and your money lands exactly where the acknowledgement promised. The invariant underneath all of it is a single ordering claim: no data page may reach the disk before the log record that describes it. Engines enforce it by refusing to write out a dirty page until the log has been flushed up to that page's own sequence number, so that recovery can always explain every byte it finds. That is the entire guarantee. The commit records, the checkpoints, the replay logic, all of it is bookkeeping in service of one rule about ordering. In practice, this is not free, and pretending otherwise would be dishonest. Your write volume roughly doubles, so a write-heavy system spends real hardware on the log, and the log device often becomes the ceiling on your throughput long before your data disk does. Putting the log on its own device is the standard first response, and it works because you are separating a sequential workload from a random one rather than simply buying more disk. Caveat: the whole guarantee depends on the device telling the truth. Consumer drives and some virtualized disks have historically acknowledged a flush before the data was actually safe, which converts your careful durability into a comfortable story. Would you know if yours was lying? There is a second dependency people underestimate: the log is a single file, and if you corrupt it, you have lost the ability to recover, not just the last transaction. This is why serious deployments check some log records and ship them somewhere else while they are still warm. Which is also the honest boundary of the idea. A write-ahead log protects you from a crash, not from a fire. It cannot help when the machine never returns, when the disk is physically gone, or when somebody deletes the wrong table with a perfectly durable transaction. Those are replication problems and backup problems, and reaching for the wrong one of the three is how teams end up with excellent durability and no availability whatsoever. Once you see the pattern, though, you find it everywhere outside databases. Your file system journals metadata the same way. A message broker such as Kafka is, at heart, a log that clients read at their own pace. Where in your own code are you already doing this without calling it that? Any service you write that must change two things at once can borrow the trick directly: write your intention somewhere durable, do the work, then mark the intention complete. Recovery becomes a matter of finishing what the previous run started, which is a far kinder problem than guessing what it managed to do. Which brings us back to the shrug. You now have a real answer for the question at the top, and it is a better one than yes or no. That payment survived if, and only if, its commit record reached stable storage before the lights went out, and it does not matter at all whether the table itself was updated. If the record made it, recovery finished the job for you. If it did not, the transaction never happened, and no half-written row is hiding in your table waiting to embarrass you next quarter. So the two things worth checking in your own system this week are cheap to check and awkward to answer. Does your storage layer actually flush on commit, or has somebody turned that off in a configuration file to make a benchmark look good? And when your log and your data share one device, do you know what your recovery time looks like after a crash under real load, or are you assuming it? The real question is not whether you trust write-ahead logging. It is whether you have ever verified the two promises it depends on, and that one is your call rather than mine.